Okay, so far we have considered soil only as either saturated or dry, and I drew this in this example. I drew a distinct groundwater table below which there is just water in the pores, above which there is no water in the pores. In reality, it's not like that. Now, if you consider the pores of a soil, especially as you go towards the finer side, your pores can get very small. So imagine your tiny pores. Of course, it has other entrances, etc. But you can imagine such tiny pores, and they are effectively no different than a tiny pore that is just a cylinder, so a tube. And if you dip any of these into a body of water, if they are sufficiently tiny, what do you get? You get capillary rise. Why do you get it? Because air-water interfaces are curved. So if we zoom into that, so let's zoom like this. So here's my tube, and here's my water and air phases. What you get here is, in this air-water interface, you have what's called surface tension. And that surface tension is everywhere, including the contact points. So at the contact, it is usually with some angle called the contact angle. And this must have been covered in your high school physics as well, if you remember. So you have your surface tension here. And the resultant force of this surface tension is proportional to the perimeter of this tube. Whereas the weight of this water that it supports is proportional to the area of the tube times height. So it's proportional to the volume of the tube. So that means as your tube gets smaller, the weight diminishes much quicker than the perimeter. So the weight diminishes much quicker than the surface tension resultant. That means in order to balance these things, in order to balance weight and surface tension, you need a much higher capillary rise. So and in the soil, the pores can be really small, so you can have really large capillary rises. Now, what things does this affect? This affects the following. First, your water can go above the groundwater level. Actually, for the sake of completeness, let's write here surface tension. So this means water can fill pores above the groundwater table. Another thing is, if I'm pulling this water up like that, if you consider the free body diagram of this curved surface, then you have a pressure of 0 on this side, in gauge pressures again. This is pulling up, and you have your pore pressure on the bottom side. To balance things, this pore pressure must be less than 0. Of course, only above the groundwater. So this thing meaning zero water pressure is still valid. Now above it, your water pressures are minus. Just as a reminder, that is gauge pressures. So that doesn't mean there is actual physical tension in that water. It is just this 0 was also gauge pressure. So this 0 was actually 100 kPa. It was 1 atmosphere. Now this is less. So maybe it is 80 kPa if you have 2 meters of capillary rise. So when we say negative pore pressures, think of it like in absolute pressures, it is still positive usually. And of course, what I said first was finer soils can have taller capillary rise zone fringe. So let's see how we can use this one in an example. Now let's have our groundwater level down here. At the depth of 3 meters. And let's say we are going to again continue our calculations down to 5 meters. And let's say we have 1 meter of capillary rise. So I'm going to give gamma dry is again 16, gamma saturated is 19, and There is 1 meter capillary fringe. Now let's mark that. Where would be that 1 meter? Think, is it above the groundwater or below the groundwater? Well, on the same page, we have the answer already up here. I have my water surface that is balanced with the atmospheric pressure here, and the capillarity occurs above that. So your capillary columns or these capillary rises are here. So let's call this 2. And let's see what happens. So let's start with the vertical total stress. So my vertical total stress will be 32 here. Then what? Then we come to the capillary zone. The capillary zone, just like these tubes are filled with water, the capillary zone is also saturated. So next, I'm going to have not 48, but 51. And then I'm going to have 89. So this 51 is 32 plus 19. And this is 51 plus 38. This is too close, so oop. So let me move it to the side here. Yeah. So let's look at the pore pressures. Up here it says dry, so let's go at 0. Now my upside down triangle, my groundwater level is here, so this is my 0. And from here, I have to be calculating my hydrostatic pressures. So here is my 20. And up as well, I have to be calculating my hydrostatic pressures. What did I say up here? I said water pressure is going to be negative in gauge pressures. So up here it is minus 10. And where does that bring us with the effective stresses? It brings us here. So I'm going to go like this. Up here it is 32 minus 0. And then we'll go through this air-water interface. Up here it is 32 minus 10, which is 42. So you actually have a discontinuity here. And then it continues from there. So here it is going to be 51 minus 0, and down here it is going to be 89 minus 20, which is 69. So capillarity also introduces some sort of discontinuity in the effective stresses and pore pressures. And this would be the case even if you had some sort of surface load. But where would the load be? So if I have load here, let's say I have some load here, and it is let's say I have some 25 kPa of stress over a large area. The reason I'm saying large area is to keep things in one-dimensional analysis, because otherwise you need to consider it in 3 dimensions, and we are not there. So here we have a 25 kPa load, so that would mean plus 25 kPa throughout this picture. So it would just be here. It wouldn't affect water pressure, and it would affect this as well, plus 25 kPa, because the water is, no matter what you do to the solids, the water is free to move within the pores. Now, so this is for the load case. So I said the water is free to move within the pores, but that might not necessarily be true. If your soil is very fine, then the pores are going to be so small that the water will have a hard time moving through those pores due to friction, etc. It will be less permeable. So if you consider from your childhood days, maybe when you played with sand in the beach, you could take some sand, some wet sand, and when you squeeze, the water would come out. So that's fine for coarse grain soils. But for fine grained soils, if you get some clay or some Play-Doh, and if you squeeze it, no water will come out. It's not going to lose its water. So we have to address that.